Hey Ross. For 6.11 on physical applications, I don't have a lot to talk about. And on our traditional assessments and final exams, we generally don't have a lot of physics. Relative velocities almost always come up. Ideas around work and torque can sometimes just come up as multiple choice questions, 1 mark multiple choice questions on a calculus and vectors final exam. But there's a couple of memory aids here that might even inform where these definitions came from. So when we're dealing with work, here's our displacement vector. We discussed in the lesson that only the component of the force that is going in the direction of the displacement is actually doing any work, which means that we have a situation, we want some sort of product that maximizes, there's theta, when theta is equal to 0. Degrees or radians, doesn't really matter. I guess we'll go degrees here. Okay. So we have some sort of operation here where you want a trig function that maximizes at 0. Well, the cosine function maximizes at 0, and you can see that here if you look at the components. This component right here would be of magnitude mag f times the sine of theta. This magnitude right here is going to be of magnitude mag f multiplied by the cosine of theta. So we define work to be mag f mag d times the cosine of theta, which is equal to f dot d, the scalar product right there. Okay. For torque, you have, say, a door or a wrench. Either way, we're looking at a top-down view. And you have some point of impact, let's say, and we use a radial vector there for the distance away. And through our experience came up in the lesson, we should understand that if you want to push a door, there's a reason why doorknobs are on the outside of the door. I don't have a funny joke. It's to increase torque. Sorry. And then intuitively, we know that you don't push on a door in this direction to try to maximize the rotation or the desire to rotate. You would want to push on it perpendicularly. Let's pretend we can't do that. So here's our applied force right here. Okay. Giving us still an angle of theta. Well, this means we would want a product that maximizes when theta is 90 degrees. Now, torque is maximized at an angle of 90 degrees, where if I'm trying to move an object horizontally and I'm pushing at it vertically, I'm doing no useful work there. Well, the sine ratio maximizes at 90 degrees. And if you take a look at how our projections would work here, this angle is also theta. And that means that this component of f going in that direction is going to be given by, am I in the wrong spot? I am. That's theta, that's theta. This component is going to be given by mag f times the sine of theta. So we get this product that is going to be affected by the magnitude of the radial arm multiplied by the magnitude of the applied force multiplied by the sine of the angle between the applied force and the radial arm. This is not quite the cross product. This is the magnitude of the cross product. I was worried about the order here for the right-hand rule. I believe I have it in the correct order though. RF torque would be downwards into the page. Often students want to know, like, what is torque? It's not really a force. Try thinking of it as just a measurement of a body's desire or ability to rotate. So this would be the magnitude of the torque vector. Should be a tau, but I can't draw a tau. That's a pretty good tau. I should be filming this. Yeah, there you go. Okay. Now, like I said, you'll see a couple, do the work and the torque homework. It'll just show you how these two vector operations can be useful where they come up. And if you plan on taking post-secondary physics, you'll be using some more algebraic vector approaches as well. So give it a shot, but if you're really confused about the nature of these quantities, I'm not that worried about it.